Okay, this is Mr. Asher, and this is for Chem 121. And what I'm going to do here is I'm going to go through the first half of Module 3, which is on ionic and covalent bonding. And I'm going to talk about ionic covalent bonding first, and then I'll have a second video on covalent bonding. And the thing you have to understand about ionic bonding is that some atoms want to gain electrons and some atoms want to lose electrons. And which ones want to lose and which ones want to gain is generally related to where they lie in relation to a noble gas. So for example, over here, you've got fluorine, chlorine, bromine, all of the halogens, which sit one space to the left of the noble gas in that column. So fluorine is one space left of neon, chlorine is one space left of argon, and so on and so forth. And when that happens, that if one of these atoms gains an electron, its electronic structure looks like that noble gas. So in one of the videos, I talked about how you build up the electronic structure of a different atom. And let me show you how that would look by turning on my whiteboard. Hopefully this will work. Yay. Okay. So for example, fluorine, its electronic structure is 1s2, 2s2, 2p5, and neon, the noble gas, is 1s2, 2s2, 2s2, 2p6. So you can see if we add one electron to fluorine, the fluorine becomes F minus, and its electron structure is now 1s2, 2s2, 2s2, 2p6, just like neon. Now, why do atoms want to do this? Well, it turns out that if you have this electronic structure of a noble gas, the electrons are completely spherically symmetric. And when that happens, they contract a little bit. And you can see this in diagrams of electron size, that the noble gases all have smaller atomic radii. And that's because once you get to the spherical symmetry here, it all contracts. They all pull together because they're happier for some reason, right? Because spherical symmetry is, I don't know, if you're believe in mysticism, it's because the spheres are some ideal concept and structure, but it really has to do just with symmetry and torques and fields and things like that related to quantum mechanical behavior of atoms. But anyway, for whatever reason, atoms want to be next to or have as close to a spherical symmetry in their electron shell as they can, right? So things to the right of the periodic table tend to gain electrons and become anions. So for example, in the top row, if we look at the top two rows of the periodic table, go all the way over here, and up here is helium, and then we have boron, carbon, nitrogen, oxygen, fluorine, and then neon. Oops, so that should go out like that. Hang on. There's neon, right? And so things over here tend to want to gain electrons, right? So nitrogen would form a N3 minus ion because it gains 3 electrons, 1, 2, 3. So it goes from 1s2, 2s2, 2p3 to, it goes to 1s2, 2s2, 2p6, just like neon. Example, oxygen will go from 1s2, 2s2, 2s2, 2p4 to 1s2, 2s2, 2p6. And the oxygen ion will be O2 minus. So that's what's going on. And so things over to the right gain electrons, and they become negatively charged ions, and a negatively charged ion we call an anion, right? Okay, so negative is an anion. And things over here tend to become anions. Carbon is sort of weird. It could go either way. It could gain 4 to become 4 minus, or it can lose 4 to become 4 plus. And we'll come back to that when we do covalent bonding and we start to look at Lewis structures and figuring out formal charges on carbon. Over here, in contrast, things that are far to the left and all the metals in here, all of these transition metals, in general, they lose electrons. And when they lose electrons, they become positively charged. So positive, and we call these cations, right? And so if we take a look, for example, at things on the far left, let's look at sodium and then magnesium, Mg, right? Well, the electronic structure of sodium is 1s2, 2s2, 2p6, and then 3s1. Right? So you can see if sodium loses this one electron here in the 3s orbital, its electronic structure becomes 1s2, 2s2, 2p6. Again, perfect spherical symmetry, looks just like neon. So sodium forms an Na plus ion, plus 1. And typically you don't write the 1 if it's a singly charged ion. Okay. Now magnesium, in contrast, magnesium is 1s2, 2s2, 2p6, 3s2. And you can see if it loses these 2 electrons here, it becomes neon. Well, its electronic structure becomes neon. 2s2, 2p6, right? And again, this is neon, noble gas, spherical symmetry, but magnesium now, because it lost 2 electrons, has a positive 2 charge, 2 plus. Okay. So that's how ions form, and it really is just a matter of where they sit to the left or to the right of the periodic table, and a lot of these why an atom will form a particular charged element or charged ion is really depending on what it's trying to do with its electron structure, and you can see this some ways in the way, where is the book? Here's the book. Let's see. Oh, this is nomenclature. Let me go back a section. This is naming ions. Okay, one more. I think it was here. Oh, come on, where was it? There was a. We'll come back to polyatomic ions in just a second. Yeah, here we go. So if you look at these transition metals, it's kind of hard to see that picture. But for example, if we take a look at the transition metals, and I'm just going to write the first row 4. I'm going across, we've got potassium, and then calcium, and then scandium, and then titanium. Whoops, titanium, come on, titanium, and vanadium, and chromium, and manganese, and then iron, and then cobalt, and then nickel, and then copper, and then zinc. I think that's zinc, right? And then if you look at the ionic charges of these, potassium is +1, which is, we understand why that is. It loses 1 electron and it looks like argon. And over here, overall here, the noble gas is argon, right? Calcium forms +2 ions because it can lose 2 electrons. Scandium forms +3 ions because it loses 3 ions, it becomes looking like argon. And now titanium can lose 2 to be either 2 plus, or it can lose 3 to be 3 plus, right? And it's a little harder to see why that would happen. But if scandium loses these 2 electrons here, and so this is 4s2, I'm sorry, 4s, 4s, 3d, 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 right? Vanadium can be +2 or plus, I think it's +2 and +3 for titanium is +2. I'm sorry, titanium is +2 or +4. Um, 4 plus. Vanadium is +2, 2 plus, or 3 plus. Chromium is 2 plus or 3 plus, or 3 plus. Manganese is 2 plus or 4 plus. Iron is 2 plus or 3 plus. Cobalt is 2 plus or 3 plus. And nickel is just +1. And then copper is +1 or 2 plus, and zinc is 2 plus. And you might start to recognize that most of these ions can have a 2 plus, right? Except for scandium, which is 3. And it's clear what's going on with scandium is 3 electrons, it's losing all 3 electrons. And titanium, what's happening is it's losing 2 electrons, or 4. So probably scandium is losing these 2 electrons, its d electrons, to form a 2 plus ion, and then 4 electrons to lose to get to the 4 plus, right? Vanadium, it would lose 3, which would lose all of its d electrons, right? Or it might lose 2, which it might lose 2 of the s electrons. Same for chromium, it loses 2 or 3. So all of these, they can lose 2 electrons, which are losing the 2s electrons. Well, the 4s2, the 2 electrons in the 4s orbital, right? But some of these are odd, and you have to understand what's going on. Is you have to look at what's happening. Like zinc can be 2 plus, and zinc has got a completely filled 3D orbital, so that's nice and happy. Whenever you get a filled set of orbitals, they become spherical. So zinc can only lose these 2s orbitals, these 2s electrons. The 2 electrons from the s orbital. They're not in the 2s orbital, they're in the 4s orbital, but it's the 2 electrons in the 4s orbital, right? And copper, you can see if it loses 1 electron. So copper, its outer electron structure is 4s2 and then 3d9. So it has 11 electrons in its valence shell. And if it loses 1, it goes to Cu plus, and then all of a sudden it has 10 electrons. And if it has 10 electrons, it can fully populate the d orbitals and they become spherical, right? And then it can lose 2, which is losing both of those from the s one. Right? Nickel the same way. Nickel has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nickel loses 10, and what happens with nickel? Somehow it rearranges things to get to a better state for itself. And a lot of what you see going on here are atoms doing this. For example, manganese, 1, 2, 3, 4, 5, 6, 7. And so if it loses 2, it has 5 electrons. And so it probably sets them into the d orbitals, loses the 2s. So that's sort of what's going on. But there's really no way to predict what these atoms in here, what their ions will be based on where they are. To the very left, if you go back to the other chart, you share. So to go back here to the periodic table, whoops, is that is that things over to the left generally tend to lose electrons to become the noble gas in the preceding row. And over here, they gain electrons to become the noble gas in the same row. So you can figure out pretty much what the ions are going to be for things to the far left or far right. In the middle of these transition elements, you just kind of have to memorize them. Zinc is +2, cobalt can be +2 or +3, nickel is only +1. So you just kind of have to know that. There's really no way to predict it. Unless you really know the details of how these electrons are moving around to populate the orbitals, which is not something we're really going to cover a lot here. Okay, now let me go back and we'll start talking about how ionic compounds form. So let's take a look at a really simple ionic compound. So let's say we've got a sodium ion and a chloride ion, Na plus and Cl. So this is positive, and this is negative. And the thing about an ionic compound is that the positive and negative charges will always balance. So the empirical or the molecular formula, not molecular, the compound formula for an ionic compound will always be charge balance. So that means that NaCl, we don't write the charges, but you get +1 from sodium and -1 from chlorine. And with that, so the charges balance. And in the compound formula for this, you will always have complete charge balance, right? So the formula for an ionic compound will always have balance. So for example, if we had magnesium, which is 2+, and then fluoride, which is 1 minus, right? We need 2 of those to balance that. So the compound formula for magnesium fluoride is MgF2. And keep in mind, there isn't such thing as an MgF2 molecule. These things exist as crystals, as shown in the book, that there's a huge crystal lattice where you've got interlaced fluorine and chlorine atoms and ions, and it's all a huge lattice. And so you don't have a, whoops, oh, and so you don't have just one molecule sitting there. That it's a crystal full of those things. And the important thing to remember about ionic formulas for ionic compounds is that the charges always have to balance, right? So if we had chromium 3 plus, and then oxide ion, which is 2 minus, right? Well, how do we figure out what that formula will be? Well, the book will tell you that's example for chromium 3 plus and oxygen 2 minus. What you do is you take the absolute value of this number, 2, and you bring it down here. So it'd be chromium 2 and bring the absolute value of that number and bring it down here, oxygen 3, right? And really what you're doing is you're finding the common denominator of these things, that you're finding something that has a balanced number of positive and negative charges, right? So the positive charges here are 2 times 3 positive, which is 6 positive. And over here, it's 3 times 2 negative, which is 6 negative, right? So the charges will always balance. And the easiest way to do it is to bring these down. Now you can run into issues, as they show in the book, where you have lead, plutonium +4, lead 4 plus, and oxygen, oxide ion 2 minus, and you bring this down and you're going to get Pb2, whoops, let me write this as Pb2O4, right? I brought the 4 down here and the 2 down here, right? But this is not to the lowest common denominator, and so you want to write this as PbO2, right? And you can kind of get from here to here in one step just by recognizing you need two things with a -2 charge to balance something that has a positive 4 charge. It's pretty simple arithmetic, but if you just bring these exponents down and then look for common denominators, it's relatively easy. So these atomic ions are relatively easy to work out the formulas for. It gets a little more complicated if we have molecular ions. And the book goes through and gives a nice table for all of these molecular ions. And let me find that, and then I will show you the, where is the formula mass? We'll get to that in just a minute. Here they are, polyatomic ions. So let me reshare that screen for you. Oops, here. Oops. So this is right out of the book, and you can see that there are all these molecular ions, and these are ions that are formed out of compounds that normally wouldn't be ionic, but when they bond together, they can lose a few electrons. So we have the acetate ion, which is really important in biology. Carbonate, this is related to CO2, and so that's another one that's important for biology, and it's critical in your body for buffering things. Hydrogen carbonate, which also goes by the name of bicarbonate, and I will almost always call hydrogen carbonate bicarbonate just because I've been doing it for so long. It's probably not going to change for me. But anyway, hydrogen carbonate is just the carbonate ion, which has a -2 charge with 1 proton or 1 hydrogen hooked onto it. So it only has a -1 charge. Cyanide ion, which is the poison. Nitrate ion, NO3, which has a -1 charge. Nitrite ion, which has a -1 charge, which is NO2. Ammonium ion, NH4 plus, so that's the household cleaner. Hydroxide ion, peroxide ion, sulfite, sulfate, hydrogen sulfate, which also goes by the name of bisulfate. Sulfate is SO4, which has a -2 charge. And that also will be a really important component of acid rain, is generally sulfate ions. Down here is hypochlorite ion, which is common bleach. Chlorite ion, which is ClO2 minus. Chlorate, ClO3 minus. Perchlorate, these are all related to bleach down here. Chromate, dichromate, permanganate. Learn these names and learn these formulas and what they look like, because a lot of the problems will have these in them, right? So if I'm sitting there talking along and I talk about, let me go back to whiteboard, your old drawings, and I talk about iron 3 chromate ions. So we have iron Fe 3 plus, and then chromate, which is CrO4 2 minus. You know that this whole thing comes together is a package as an ion with a -2 charge. So we're figuring out the formula for this. We would bring the 2 down here, so we get iron 2, and then we would have in parentheses CrO4, and then below that would be 3. So we get 3 -2 charges from chromate, 2 negative charges for 6 negative total, and we get 3 positive charges for a 6 positive from the iron. So this is charge balanced, right? But remember, there's no such thing as a Fe2CrO4 free molecule. It's a big crystal, and each part of the crystal has that average composition, or that composition in terms of ions. Okay. Now, the other important thing about ions is that we can determine what's called a formula mass, and we do that in terms of the atomic mass units of the component atoms. So let's look at, for example, the formula mass for a simple salt, which would be NaCl. Really pretty easy. And so for that, you're going to need a periodic table. And so you can find one, and to figure out what the formula mass is for this, you need to figure out the atomic mass of sodium, which is 22.990 atomic mass units, AMUs. And then chlorine is 35.453 AMUs. And then you just sum them. So 3, 4, 4, 8, 5, 58.443. And this is the formula mass for NaCl. And let's look at that other compound we had, which was Fe2CrO4 3, right? So this is iron 3 chrominate. We would name this as iron, and then in parentheses 3 because it's the trivalent ion of iron, so ferric iron 3 chromate. And so iron, the formula weight for iron is 55.845. And chromium is 51.996. And oxygen is 15.999. And now we have to figure out, so this is chromium and this is oxygen. And we have to figure out how many atoms of each of these we have in one of these formulas, right? Well, the little 2 here means we've got 2 irons, so this is times 2. And here, there's 1 chromium, but see, there's 3 chromates. So that means this is times 3. And this is 4, 1 times 3. And this is 4 times 3. Excuse me for just a minute. So this is 12. So there are 12 oxygens in this formula. See that? You get 4, but there's 3 of them. It's like I'm buying hot dog buns, and I buy 5 packages of hot dog buns. Each one contains 8 buns, but I buy 5 packages, so I get 40 buns. Here I bought 3 packages of 4 buns, so there's 12 buns. I got a dozen buns, right? Okay. So this is 2, 3, and 12, and I multiply each of these by the atomic mass. So 12 times 15.999. And this is 191.988. And then 3 times 51.996 is 155.988. Oh, look at that. And then 55.845 to 11.690. 11.690. And you add them all up, and you get the formula mass for iron 3 chromate of 459.666 AMU. Okay. Hopefully that's relatively clear. I'm going to stop there because I think that's most of what we need to do. And I think a lot of this is pretty straightforward in terms of understanding how to do nomenclature of these things. A lot of it is just memorization. And unfortunately, that's just the way it goes. There isn't a lot of mnemonics you can use. I don't know of a handy mnemonic for figuring out what the ions are. Just remember that when you're naming ions, they the book goes through it, but the easiest way to do it when you name ions is not to worry about whether it's ferric or ferrous, but just use the IUPAC standard and say that it is iron 2 or copper 1, right? just put the oxidation state in there, the charge there in the numeral, rather than try and remember whether it's cupric or cuprous ion, right? So anyway, so that's how it works. You want to memorize the more common molecular ions so you recognize them, so that if you see a formula that is like Na2, what's the formula for Na2? Na2, I'm sorry, NaC2H3O2. You recognize this as sodium acetate, and it would be ionic. Okay. Anyway, that's all I got for this part. I'll record something about covalent bonding, which is a little more complicated next, and I will talk to you later.